Welcome back to Multimedia course INFO430. Today we will continue the course outline and we arrived at a chapter entitled Fundamental Concepts in Video. This is chapter number 5 in the textbook we are following, and today we will see 3 sections about the fundamental concepts in video. This chapter will not discuss the video compression standards, which are discussed in a later chapter in detail. But before we go to the compression, to MPEG compression, we have to study these fundamentals and to be aware of them. So first we will see the analog video, and in this section we will introduce what is a video signal. Up until last decade, most TV programs were sent and received as an analog signal and not as a digital signal like the case today. So once the electrical signal is received, you may assume that the brightness is at least a monotonic function, because if it was not a linear function, we know why, because it has been subject to the gamma effect. Okay, what is an analog video? A progressive signal is a signal that is a function of time, because this is video, this is not still image, that samples a time varying image. So the image will vary across the time. So this signal will sample this time varying image. How? It progressively scans, traces, okay, through a complete picture, a frame, row-wise for each time interval. So for a time interval from t to t plus 1, for example, you scan the rows of this image, and until the next time interval, you have the image that it was changed. So you go back, like you can see the vertical retrace, you go back from the last picture element and you repeat the scanning beginning from the first picture element, and you go row-wise again, and this value is a function of the time, and this is the analog signal f of t. And here what we described is the progressive scanning. Okay, so you scan the complete frame row by row, and in each row value by value. Another mode of scanning is called the interlacing. What is the interlacing? In this time, we also take the values of the picture element of the frame and through time, but this time we don't take them progressively one after the other, but we trace lines all odd and then all even. So as you can see, here's a line, some of them are dotted and some are solid. We trace all the solid from P to Q, from R to S, etc. until we arrive until the point T. And this is half of the frame, because we skipped lines, we skipped the even lines. We go back and we trace from U all the dotted lines until the point V. And this is how, by two tracing, we finish a frame. So a frame is traversed into twice, into two times, and will be composed of two fields, and we call them the odd field and the even field. And this way of tracing, of course, there is a horizontal retrace, like the progressive. Whenever you arrive at the end of the line, you have to retrace horizontally to the first picture element in the new line, and go forward tracing until the end of the line. This coming back at each end of the line is called horizontal retrace. And the vertical retrace is what? In this case, the vertical retrace is when you go to the end of the picture and you want to retrace again, because you want to trace the other field if we are in the interlacing mode, or you want to interlace the next frame if we are in the progressive mode. So The horizontal retrace is the jump from, for example, Q to R, from Q. Let us see here. This is Q, the end of the line, to the next line, to the beginning of the next line, or in this case, because we are talking about analog signal, the electrical beam in the CRT in the screen will not be enlightened, will be blanked, because you don't want to see the retrace, you only want to see the tracing. Okay, so we turn off, if you want, the electrical beam until we go back to the beginning of the new line and we turn it on. Why we are talking about this? Because next we will see standards that will tell you some values for the properties of these things. So we will be telling you how much in this standard we allow the vertical retrace to take time, how many frames per image we will be showing on the screen, how is it interlacing or not. So you have to get used to these terms. So we discussed the retracing, the vertical and horizontal retracing, and in this image we see the video raster including the retrace and sync data. What is this? Not all the data that we send and receive are image data. You know now that some of them are for vertical retrace, some of the part of the signal is encoded the vertical retrace and the horizontal retrace. And you know that before each line you have some values that were sent because the tracing was going in horizontal retrace. So the encoding was going back in the line. And the same thing for the beginning of every frame. We have the vertical retrace. So when we were in the end of the frame, we wanted to go back up, and this took time, and for this we sent special values for the signal. And these values, when received, they won't be displayed on the TV because the screen knows that those are special values, for example, low signal values or negative signal values. And as we said, the electronic beam will be turned off or blanked. So why do we interlace at the first place? Why did we came up with this idea to divide the picture frame into two fields, odd and even? Interlacing was invented because when the standards were being defined, so at the time when the standards were being defined, remember, it was not today, it was difficult to transmit the amount of information in full frame quickly enough to avoid flicker. So the frame rate was, we were obliged to define the frame rate a low value. Not like today. Today we can transmit 60 frames per second or even 120 frames per second. But at the time we were limited by the bandwidth, by the every parameter. So we saw that if we double the number of fields presented to the eye, it will reduce the flickering perceived by the eye because of the late coming of the new image. Okay, because every image took time to be replaced by a new image, so they thought that if we send the odd field and then the even field and then the odd field, it's like sending a new image every half the time, and this will give a feeling of continuity for the image, for the video, and the flicker will not be perceived anymore. So this is the idea about interlacing. And as you will see in this chapter, at the end of this chapter, we returned back to progressive mode. We are at ease. We don't have this restriction anymore. Aliasing. Because of interlacing, odd and even lines are displaced on time from each other. We scan the video first to take the odd lines, then we scan it together to take the even lines to trace the image, even lines. And remember, a video is a moving picture. So from the time we took the odd lines to the time we want to take the even lines, the objects in the video have moved. So generally, this is not noticeable except when very fast action is taking place on the screen. Like in the example, you have a helicopter. So every part of second, the helicopter moved, it changed its place. And this is an example of blurring. So this is aliasing. This is blurring where it may occur. Example, in this moving helicopter, if you take the field 1, the odd field, and the field 2, which is the even field, and those are two matrices of the same dimensions, because this is half the frame and this is half the frame, half the lines and half the lines. If you subtract them, you will not have zero values, because, and especially where the movement was fast. So you have the zero values everywhere, unless where there is a boat, you have white values, high values, and where there is helicopter, and especially where it moved fast, the parts of the helicopter that change their place. And look here how much it changed. And this is the aliasing effect. The aliasing effect is noticeable by the eye. What is the deinterlacing? Sometimes, just like we did an interlacing, we need to do deinterlacing. Why? Because sometimes we need, for example, to change the frame rate. The frame rate is the number of frames we send per second. Sometimes we decide that we can afford a higher frame rate, so we do the deinterlacing, and then we do the interlacing again, or for example we do the progressive mode because we have enough bandwidth. Or sometimes we need to do the resizing. We need to get the complete frame, not the two fields of the frame. So when we want to get complete frames from the fields, the odd fields and the even fields, and remember that those fields are not parts of the exact same image, they are part of the moving image, so it may have changed from the time of taking the odd field to the time of taking the even field. This process to join them is called deinterlacing. The simplest deinterlacing method is, of course, to discard one field, just throw it in the garbage, and duplicate the scan lines of the other field. So just like we are making every line, we are doubling it. We are, of course, making thicker edges. And the information in one field is lost completely. This is the brute force. This is the most easy. But of course, there are other more complicated methods that may be used, and this depends to the end of the deinterlacing. What you want to do with this deinterlacing. So now let's see let's remember what is the aspect ratio. It is simply the width to the height, the ratio of the width to the height of the image on the screen. So on the left, you can see an image of aspect ratio, which is a very famous aspect ratio, 4:3. So you have for 4 centimeters, suppose, or 4 inches, or 4 meters, 4,000 pixels in the width, you have 3 for the height, and this is the aspect ratio for 3. And another very known now aspect ratio is the 16:9, and there are other aspect ratios. Also, we introduce this concept because we know that later in this lecture we will be referring to aspect ratio. Again, I explain why, because I will say, for example, the standard NTSC uses the aspect ratio for third, for example. So, and here we come, we study first, we are still in the section analog video, and we arrived to the first analog video standard, which is called NTSC. You remember this standard because we mentioned it in the chapter color when we said that NTSC, when we divided the word map and we indicated where the NTSC standard was used. We didn't explain it, but we explained that it used a color model, and that's why we explain it. We mentioned it, sorry. So, this is the National Television System Community. This is the National Television System Committee, and this is a TV standard mostly used in North America and Japan, and it uses the aspect ratio 4/3, and in which there are, in each frame, there are 525 scan lines. Okay, so this standard defined that in my frame, in my video signal frame, there are 525 scan lines, and I am sending, or this standard is sending 30 frames per second. So each second he will be sending 30 frames, and to be more exact, it is sending not 30 complete frames, but 29.97 frames per second, which is in another way, which is sending 37 milliseconds per frame, which is every frame to be completely sent, it needs 33 milliseconds. Okay, and this video standard, because this was one of the first, of course needed to use the interlace scanning system, and in which each frame was divided into two fields, and this gives me half the number of the lines for the first and half for the second. So this gives me 262.5 lines per field, and you know where does the half line comes from, because you remember from this slide that the odd fields ended in the middle of the frame width, and the even fields begin in the middle of the frame width, because the lines are not totally horizontal, they are slightly benched. Back to our NTSC slide, we continue the standard description. So in the standard, we said aspect ratio, how many numbers per frame, how many lines per frame, how many frames per second we are sending, is it interlaced or not, and then we say horizontal sweep frequency is, of course, it's a simple calculation. It's how many lines, because we said we are sending 29.97 frames per second. So how many lines per second? The number of lines in each frame times the number of frames, and this will give me 15,734 lines per second. So if I ask now, how many seconds will it take me to send every line? It is 1 over 15,734, and in seconds it will have lots of zeros, so I will express it in microseconds. A microsecond is 1 to the power minus 6 seconds. So each line is swept out in 63.6 microseconds. And do you remember the horizontal retrace? The horizontal retrace takes time to be done, and it will take, in the NTSC video standard, it is allowed to take 10.9 microseconds. So if the horizontal retrace takes 10.9 microseconds and all the line takes 63.6 microseconds, so what is the active line signal time the active line signal time is the difference. If sum of the time is for the horizontal retrace, then the remaining time, the 52.7, which is 63.6 minus 10.9, is called the active line signal, during which the image data is displayed. Okay, so this is for the active line signal. This is a small calculation so that you can understand where do the numbers come from. And the analog signal with no fixed horizontal resolution, so we say that in the NTSC you have 525 scan lines, but we didn't say how much the horizontal resolution is. And there are different video formats that provide different number of samples per line, and we see some of them here. We see the VHS, the SVHS, the Betamax, the standard 8M and the high 8mm, and in which everyone is different. This is a small exercise. We have an NTSC video that has 525 lines per frame, and we know that it takes 63.6 microseconds per line, with 20 lines per field of vertical retrace. So you remember the vertical retrace in the beginning of every frame. We have 20 lines per field of vertical retrace, and 10.9 microseconds horizontal retrace. And the question is, where does the 63.6 microsecond come from? And you know that if we go just one slide, they come from, we divide 1 second by the number of lines. This is the time that takes one line to be transmitted. Question number B, which takes more time, the horizontal retrace or the vertical retrace? But we said that one line takes 63.6 microseconds, and we said that the horizontal retrace, they already gave us, it takes 10.9 microseconds, and then we said the vertical retrace has a duration of 20 lines per field. So this is the vertical retrace is going to take time 20 times 63.6 microseconds, and is of course greater than 10.9 microseconds. We arrive at the PAL video, and this is another standard, as you can remember, and this is an abbreviation of phase alternating line, and this is a TV standard used in Europe and China and India and many other parts of the world. In this standard, unlike the NTSC, and in parallel, they were defined in parallel, so it uses more lines per frame. It uses 100 more lines per frame, and but for the price of reducing the number of frames per second, because we are limited. So instead of sending 30 frames per second, it will be sending 25 frames per second. It will use the aspect ratio for third, the interlaced fields, and it will use the YUV color model and not the YIQ color model as in the NTSC. Okay, so we know that. And in this video standard, we have 8 megahertz per channel, and in which we allocate for the luminance 5.5 megahertz, and for the chrominances, which are U and V, we allocate 1.8 megahertz. And this is discrimination. Why on the earth we allocate more megahertz to one channel than to other two? So we have 5.5 megahertz to the Y channel and 1.8 megahertz to each of U and V channel. So why less? Because we will talk later, we will talk just right now about chroma subsampling. So we don't send all the channels of U and V, we subsample them, we send parts of them. Why? We will explain why. And this is also valid for the NTSC standard and for the SECAM standard. Okay? So chroma signals in this PAL video standard uh, have alternate signs, and this is where the name came from, phase alternating line. So we send them one time positive value, one time negative value, and this technique facilitates the use of line rate comp filter at the receiver. So the receiver, in order to take the Y value, he will average the signal, so he will eliminate the opposite values for chroma, and what will remain is the high quality Y signal. Okay, in the SECAM vidéo standard, Système électronique de couleur avec mémoire, SECAM, this is a third major broadcast TV standard in which, as you can just remark, it uses the same parameters as the PAL video standard. 625 scan lines per frame, 25 frames per second, 430, and interlaced video. So PAL and SECAM are very similar. They differ only in the color coding scheme. So SECAM uses U and V signals, but they are modulated differently using separate color subcarriers at 425 MHz and 441 MHz respectively, and they are served in alternate lines, and only one of U or V signals will be sent on each scan line. So the difference in the coding of the colors. Here we can find a comparison of the analog broadcast TV systems. You can see in this table the NTSC TV system, the PAL TV system, and the SECAM TV system. Okay, for the frame rate, the NTSC we all know 29.97, the PAL and SECAM 25 frames per second. As per the number of scan lines, the NTSC 525, the PAL and SECAM 625. As for the number of total channel widths in megahertz, the NTSC it dedicates less megahertz for the channel width, less than the PAL and SECAM, which dedicate 8 megahertz for the channel. As for the bandwidth allocation, the three standards allocate more bandwidth, more megahertz for the wide channel, and we said we will explain why we do the chroma sampling, why we give the chroma less bandwidth. But the NTSC gives 4.2 from the 6 megahertz all for Y, the PAL 5.5 for Y, and the SECAM 6 MHz for Y. The NTSC gives 1.6 MHz for the I channel because it uses YIQ color model, and 0.6 for the Q channel, while the PAL gives two equal bandwidths for the U and V channels, but it is alternating, it is in opposite signs, and the SECAM gives 2 megahertz for each U and V. So this was the comparison, and next section is the digital video we will see. Section 2 in this lesson is about digital video. So we saw the analog video, and now we will continue to explain the digital video. So the digital video has many advantages, and let us see them. Video can be stored on digital devices or in memory ready to be processed. So we can process it, we can remove the noise, we can cut and paste, etc. So this is video processing. So if the video is digital, it is stored on the devices and it is ready and integrated to various multimedia applications. You can have direct access, which makes nonlinear video editing achievable as a simple rather than a complex task. You remember, or maybe you don't remember because you didn't use them, but the analog video decoders, when we used to watch an old video and you want to skip to go to the middle or to the end, you have to rewind and advance progressively. You cannot jump into the next chapter directly, just like you have a DVD or you are watching YouTube. You, in one click, you jump, you are at the end of the video. So this is achievable with digital video, and it was not possible with analog video. And another property is that if you repeat the recording on the same tape, because after all it is not an analog support, it is also a digital device. If you repeat recording on the same hard disk, on the same memory space, it will not degrade the image quality. It will not degrade the quality of the signal, because this is also in digital world. And the last point is that digital video, ease of encryption, and better tolerance to channel noise. So, in the first concept we will discuss in the digital video is the chroma subsampling. Since humans see color with much less spatial resolution than they see black and white, and we discussed this concept and this notion in the chapter of colors, and we explained why we changed from the RGB channels to color models that are more convenient to the perception of humans. It makes sense to decimate the chrominance signal. So if we know, and we already studied and discussed, that the humans cannot perceive as accurately the chrominance channels like they perceive the luminance channels, so it makes sense to discriminate the sending of the two channels. Why? Because we were limited in bandwidth. We cannot send all the information that we dream of sending. We have to reduce the volume of the data that have to be transmitted. Even if it's not transmitted via network, even if it's only transmitted from the device, the decoder of the video, to the screen, the cable that transmits the signal has a limited bandwidth, and the decoder and the encoder has limited processing capabilities. They cannot process a huge image in order to show you on the screen and a real time. What does it mean in a real time? If I am talking now, I am recording a video, it takes me, for example, 1 minute to record it. You want to see it in 1 minute, if not less. So you don't want to see me saying, you don't want the person to talk slowly, to move slowly, etc. So you want the real time effect. So in order to accomplish this real time effect, the scientists were obliged to reduce the volume of the data. So, the numbers are given stating how many pixel values per 4 original pixels are actually sent, and we will be seeing now interesting but not necessarily informative names that have arisen to label the different schemes used. So, we will be seeing now schemes of subsampling, different methods of subsampling, and different conventions. Okay, we will see now the 444, the 422, and the 411, and the 420. And these names, we call them weird because they don't really help us to remember every format, every subsampling scheme. What does it make? Okay, we will begin, and hopefully we will remember that the 444 subsampling scheme is the scheme of no subsampling. For every 4 values, I will send the 4 values. Okay, if I have 4 values of y, 4 values of v, and so values of u, I will send them all 4, 4, 4. You will think that this is easy because for 444 this is easy, but for the other names it's not that simple to express them. Okay, we will go to the, or we said for UV, and we can, you know that we can say why CBCR also, because the important thing is that we have a luminance channel and two chrominance channel, and the chroma subsampling affects always the chrominance channels and never the luminance channel. So let us look more on the schema. You can see here that the plus signs represents the luma subsamples, and that the circles that are in red will be representing the chroma subsamples. And when we say chroma subsamples, it means CBCR if the color scheme is YCBCR, and it means UV if the color scheme is UV. So whenever you see a circle red, it means that this is for CB, and also the same for CR. So we return back to the 444 schema, and we see for an image we are representing every cross and every circle. It means as is the image, the frame came to us, we send it all to the other side. Okay? And this is one. And the 422, it means, look here, we always have the cross. In the four schemes, we always have 4 by 4 crosses. So this is the matrix we are taking as an example. 4 pixels width, 4 pixels high. For every scheme, the luma we don't touch. We send as is because the human can perceive the reduction in the subsampling in the luma, so we don't touch it. What we touch is the chroma samples. In the 444 scheme, we don't touch them. This is a complete scheme. In the 422 scheme, we send a chroma sample, one yes, one time yes, one time no. Okay? So if we have a 4 by 4 initial matrix, if we have an initial matrix of 4 by 4, we will be sending a luma matrix of 4 by 4, but we will be sending two chroma matrices, each of which, because one for CB and one for CR, but the one for CB will be 4 lines, 2 columns, and also the one for CR is 4 lines, 2 columns, because we skipped one column every factor of 2. Okay, so and we continue the 411 subsample horizontally by 4. So for every luma, 4 luma subsamples, we send only one chroma subsamples, one chroma for each channel, one chroma subsample for each channel. For the initial matrix 4 by 4, for the luma, we will have the third channel 4 by 4, but that's the first channel will be 4 by 4, but the second and the third channel will be 4 by 1. And the 420 color scheme, also for every 4 luma samples we will have one chroma sample, but unlike the previous one, we will have them for every 2 by 2 submatrix. We will have the average of the chroma. We will send one average chroma, and not like in the 411 subsampling we used, for every line we send samples, but for every 3 columns no, one column yes. In 420 we skip one line, one column every time. So this is the subsampling technique, and the subsampling technique, instead of sending 3 matrices each of size 4 by 4, suppose, or n by n, we send 3 by matrices, the first of size original, but the 2 other of either half the size or even quarter the size of the original, and this is for the the two other channels. So this is reducing by a huge number the amount of data. This is reducing by the half the amount of data that is sent over the bandwidth. In this slide, we are seeing the ITUR digital video specifications, and those are also some standards we will be studying, we will be seeing. But first, we already know the NTSC, we know the PAL, SECAM, because they are close to each other, but this is now in digital video representation, not analog video representation. We will introduce the CIF and the QCIF. But for the CIF, we will introduce the name. Where does the CIF name came from? This is Common Intermediate Format, proposed by CCITT, which is the International Telegraph and Telephone Consultative Committee, that became now the ITU, the International Telecommunication Union for both telecommunication and radio frequency matters. So we have one name, ITU, and the idea of CIF is for the VHS quality. What is it? We wanted a format to lower the bit rate because we wanted a progressive and non-interlaced scan, and we wanted a low bit rate. And then we have the QCIF, which is the quarter of the CIF, and you will notice here the QCIF image width and height, frame width and height are half by half, so it is 1/4 of the overall resolution of the image, and is for even lower bitrate. So QCIF was first introduced in the first video conferencing, when you need to have a video conference just like now Zoom and Skype and everything, but you really don't have a bandwidth. So they invented this standard to be able to send videos, but for lower bit rates. CIF and QCIF resolutions are evenly divisible by 8, all except 88 divisible by 16, convenient for block-based video coding in H.261 and H.263. H.261 and H.263 are standards, are methods that we will be studying in the video compression chapter, and they are very important standards. Okay, so and you will know when we study them that we divide each frame by 8 by 8 blocks. So if I have a frame 512 pixels width, 512 pixels height, I will subdivide it into blocks of 8 by 8 or 16 by 16 in order to apply video compression that we will study later. So those two standards were, they kept in mind this thing, and that was used. Okay, let us read this table, and we will retain it. For the luminance in the NTSC, we had 720 times 480. You see the numbers changed in the digital video format. For the PAL SECAM, we have the same width but a higher number of lines. For the CIF, you see that the resolution, the width per height is less, and the quarter for the QCIF. And now you can understand that because of the subsampling 422, the size of the chrominance resolution is half. Okay, is half in number of lines, because in the 422, the width is the half. So this is the width, but the number of lines are the same. And the same thing for the PAL. It uses the subsampling 422, so the width is divided by 2. And for the CIF, we are using here the 420, so the width is divided by 2 and the height of the chrominance resolution is divided by 2 relatively to the luminance resolution. And this here I can easily say this is a good question for the final. If I give you some missing parts of this matrix, you can easily fill it. This is a very easy question. What about the aspect ratio? The aspect ratio is 4/3 in all the four digital format, and the number of fields per second, you can see that we have 60 fields per second for the NTSC because this is interlaced, and we have 30 frames per second, so of course we will have 60 fields per second, and 25 will become 50 because it's the double. And for CIF and QCIF, it is not interlaced. Those are two progressive video standards, and that's why we have 30 frames per second, 30 fields. One field is one full frame. So this was about our early digital video standard, and then came the high definition TV. And the main thirst for the high definition TV is not the high definition, it's the high size. So the main thirst is not to increase the definition in the term that you understand definition, the colors of the pixels, and the reality of the image in each unit area, but to increase the visual field, especially in its width. So we wanted a larger screen, a bigger TV. First generation of HD TV was based on an analog technology developed by Sony and NHK in Japan in the late 1970s. And then we have Muse, which is multiple sub-Nyquist sampling encoding, was improved, and was an improved NHK HDTV with hybrid analog digital technologies. So they used not only digital technologies, also hybrid technology that was put in use in the 1990s. And with the HDTV, we have, instead of, for example, 480 or 525 or 625 scan lines, we can talk about 1125 scan lines. First, they were interlaced, so we have 60 fields per second, and the aspect ratio becomes 16:9 instead of 4/3, so the screen is wider. The uncompressed HDTV demand was that we can have greater than 20 MHz bandwidth and will not fit in the current 6 MHz or 8 MHz channels defined in the NTSC standard and in the PulseCam standard. So they began thinking, how we will make the 20 MHz fit inside the 6 MHz or the 8 MHz. We have to compress the data. We cannot send the data. Even with chroma subsampling, the data will not fit inside the 6 MHz channels. So various compression techniques begin to be investigated, and the HDTV signals will be transmitted using more than one channel even after compression. So even after compression, we needed more bandwidth. We continue the HDTV, and we say that for video, MPEG-2 is chosen as the compression standard. So when the HDTV came, we studied the video compression. And for audio, because remember, the video signal contains also audio, not only moving image, we chose the AC3 standard that supports the so-called 5.1 channel Dolby surround and 5 surround channels plus a subwoofer channel. there is silent difference between the conventional TV and the HD TV, and you already noticed that HD TV has a much wider aspect ratio, and HD TV moves towards progressive and non-interlaced scan. Interlacing introduces serrated edges to moving objects, and we already said that flickers come along horizontal edges. This table shows us here the standards for video, and you can see now also that came into play also the HDTV. We can see that the luminance resolution is 1920 times 1080 in comparison to the others, and it's a huge resolution. And the chrominance is subsampled because we use the color subsampling 422. We have 120 fields per second. We have 60 frames per second. It is interlacing and it has the aspect ratio 16:9. So this is now the place of the HDTV inside the table. And we continue to see another table that is entitled Advanced Digital TV Format Supported by ATSC. What is ATSC? So the boom of the proposals for the digital video HDTV led the Grand Alliance to be created. What is the Grand Alliance? The four big companies, the General Instruments, the MIT, the Zenith, and the AT&T, they said we will do the Grand Alliance. Let us gather our efforts and go with one standard. And then they had also joined Thomson, Philips, Sarnoff, and other leading companies in the field. So what was born? The ATSC, the Advanced Television Systems Committee. So let us see this table now. Those are available TV formats, advanced digital TV formats. We have a certain number of formats. We have the first format, which is 1920 pixels width and 1080 pixels height, aspect ratio 16:9, and we have different possible picture rate: 60 progressive, 60 interlaced, 30 progressive, 24 progressive. And we have other also formats: 1280 times 720, and we have also other lower formats. And then after the HDTV came the ultra high TV. The ultra high TV took the standard to a new level. This is a new generation of HDTV that was announced in 2012, and it has two main support. It supports the 4K UHD TV, which has 2160 progressive, which has 3840 times 2160, which is progressive scan. And we have an even bigger one, which is the 8K UHD TV, which is 7000 times 4000 progressive scans. This is huge. This is really huge for cinema. And in both formats, the aspect ratio is 16:9, and the bit depth is up to 12 bits for every channel, and you can have the chroma subsampling 420 and 422. The supported frame rate is 120 frames per second, and they are progressive. Remember, they are progressive, not interlaced anymore. and we have a superior image quality comparable to IMAX movies, and which requires a higher bandwidth and of course a higher bitrate. In 2013, the ATSC that we just mentioned here, the ATSC, called for proposal to support the first scheme, the 4K UHD TV, which is 2160p at 60 frames per second for a first start. Here is a small comparison between the early YouTube video. Remember the early YouTube video, it was 320 times 240, and then you can see the NTSC, which is has less lines than the PAL, and you can see the H720 and HD720. You saw here the HD720. And then we can see also another HD format, which is 1080 lines. 1080 lines. Sorry, the HD720 is 1280 columns. And then you see the screen sizes, the comparison between the screen sizes. This is really impressive. So this is the 4K, and wait until you see the 8K difference in resolution. So we finished the second section. It was about digital video, and next we will see the video display interfaces. So let us continue our lesson and finish those 8 slides with the last section of the lesson, which is entitled Video Display Interfaces. There have been a wide range of video display interfaces supporting video signals of different formats, analog or digital, interlaced or progressive, different frame rates, and different resolutions. And we begin by seeing the analog display interfaces, and then we will see the digital visual interfaces. So the analog display interfaces, we have connectors for typical analog display interfaces, and we study 4 of them. First, we will see the component video. You see here the three cables, and the composite video, which is all in one only cable, one signal, and the S video. Okay, this is separates the luminance and the chrominance, and lastly the VGA. As for the component video, 3 separate video signals for the RGB planes. It can be also for other planes, YCBCR, YIQ, so the 3 channels each on a separate signal, and this is very good for analog interfaces. It has the best color reproduction, and there is no crosstalk because each signal on a wire, and it requires bandwidth elevated, of course, and it requires synchronization because every signal is alone. Say they arrive, we have to synchronize which value with which value, and if some are lost, we have to see what to do with the other 2 channels. Another interface is the composite video, which composes all the 3 channels into one signal. So 2 chrominance and one luminance, they have all on the same signal, and they are mixed together into one carrier wave, and you put the chroma at the high frequency in order to be separated later at the receiver end. But for sure this will cause interference, and this is the second type. The third type is the S video, which said, okay, we will use only 2 signals. This is a compromise between the component video and the composite video, and don't regard at those 2 wires. This is not it is this one. the S video, okay, and this will cause less crosstalk. We have our very important Y channel alone, and the others are the chroma channels. It's okay to mix them. So the more crucial grayscale information is separated from the chrominance. And we have also the VGA, the Video Graphics Array. It was introduced by IBM in 1987 with its personal computers too, PS2, and the resolution was initially 640-480 using 15 pin. Then it became bigger and the bandwidth became bigger until now we have VGAs for the QXGA resolution, which is 2048 times 1536 with 85 Hertz and 388 megahertz. The signals are based on analog components, so VGA is for analog signals, and it has the channels RGBHV, which stand for red, green, blue, and horizontal synchronization and vertical synchronization, because you have to synchronize all of this. And it carries a DDC, which is a display data channel, and the data defined by VESA, which stands for the Video Electronic Standards Association. We will talk about VESA later also in the digital video connectors. This suffers from interference when the cable is long because they are all inside one cable. Another kind are the digital video connectors, display interfaces, and they emerged in the 1980 with CGA, which is the color graphics adapter. Digital visual interface, DVI, high definition multimedia interface, HDMI, and the display port are three kind of those connectors, okay, and we will see them here. We will begin by the digital video interface. It was introduced by the Digital Display Working Group to transfer digital video signals from computer card to the monitor. It was intended to deal with uncompressed digital video. Okay, we will connect uncompressed digital video and support multiple modes: DVI-D for digital, DVI-A for analog only, or DVI-I for digital and analog. And it was conceived to be backward compatible with VGA. So if you need to convert from VGA to DVI or vice versa, you can plug an adapter. The transmission format is based on panel link, which is a high-speed serial link technology using TMDS. What is TMDS? It is transmission minimized differential signaling. The video card reads the display's EDID, which is the extended display identification data, and then it chooses the preferred mode or native resolution. The single link mode, it has maximum pixel clock frequency at 165 megahertz and the maximum resolution at 2.75 megapixel at 60 hertz refresh rate, so 60 frames per second, and the maximum ratio is 16:9 screen with the resolution of 1920 to 1080 columns at 60 Hz, and the dual link with a higher resolution, of course, going from 2050 500 to 1600 at 60 Hz. High definition multimedia interface, you all know the HDMI cable. This is a newer digital audio video interface that is conceived to be also backward compatible with DVI by the consumer electronic industry and widely used since 2002. 2. The specification is identical to those of DVI, but the difference is it only supports digital, no analog signal, and VGA incompatible. So HDMI is incompatible with the VGA, and the color space is limited. In the DVI, in the previous connector, it was limited to RGB. In the HDMI, it supports RGB, YCBCR, and the schemes, the subsampling 444 and 422. And it supports digital audio. And there are versions HDMI 1, HDMI 3, and HDMI 2. The final one is the DisplayPort, which was introduced by VESA in 2006. It first display interface to use packetized data transmission like the internet or the Ethernet, and it was based on micro packets and can embed clock signals and higher resolution with fewer pins, okay, in the DisplayPort. It is extensible, so when you have to add new features, they can be added over time without significant changes to the physical interface itself. So this is good, and it can transmit audio and video, or audio alone or video alone. Of course, it will dedicate all the bandwidth to the signals in this case. The video signal pass 6 to 16 bits per color channel. The audio pass up to 8 channels of 24 bit of 182 kHz of uncompressed PCM audio or compressed audio, and dedicated bidirectional channel carriers, device management and control data. To replace VGA and DVI, this DisplayPort was introduced by VESA to replace VGA and DVI higher video bandwidths. It was enough for 40 simultaneous 1080 progressive 60 Hz displays. Okay, imagine. Or for 4K video, which means HDTV, UHD-TV video at 60 Hz. So this is a good connector, and it is backward compatible to VGA and to DVI. Okay, and if we compare it to HDMI, which one is better? DisplayPort has more bandwidth. It accommodates multiple streams of audio and video to separate device. VESA specification is royalty free, but HDMI charges an annual fee to manufacturers, so this is not free. So this is a big advantage to DisplayPort over HDMI. So expect it to be used instead of HDMI, and it began. And this was about our lesson, and if you are interested, you can continue the textbook chapter, and you can read about one interesting subject, which is 3D video and TV, and 3D pictures and movies were there from since decades, and they enable the experience of immersion. But the rapid progress in research and development of 3D technology added to the success of the Avatar film in 2009. It made the peak of the 3D technology. But unfortunately, we will not study it because it is out of the frame of this course. You can read it. This is a good reading. See you next in the chapter of compression, lossless compression techniques.